In this video, we're going to talk about the electric potential energy due to point charges. The equation that shows the relationship between the work done by a conservative force and the change in the potential energy delta U of a system is the work is equal to the opposite of the change in potential energy of the system. You might have seen a similar equation, actually an identical equation, when you studied some mechanics. That equation is an important one in physics. Here's another one that's important. The equation that gives the potential energy U associated with the configuration of two charges QA and QB is very similar to Coulomb's law, except Coulomb's law has R squared in the denominator and the potential energy only has R. Be very careful of that. All right, we're going to use that equation here in a bit. Let's say that we have these four charges. Three of them you can see are positive. The one in the lower right, Q4, is negative. We're going to build this system. If we begin with no charges, then the total potential energy that we have is 0. We haven't built this system yet, but we're going to. And we're going to mentally bring each of these charges in from the distance of infinity. But when we don't have any charges, obviously, we don't have any potential energy. Now, from infinity, we bring in only charge Q1. So here we go. We're pulling it in. There are no other charges around to exert a force on Q1 as we bring it in. So there's no electric force that applies. Thus, the work that's done is 0. And if the work that's done is 0, then the amount that the potential energy has changed by is 0. And that means that the total potential energy stored in this system is 0. Oh, everything's 0. Easy so far. Now we're going to start dragging the other charges in one at a time. And what I've done here is I've put a 1, 2, 3, and a 4 because that's where the charges are on our original picture. I didn't want to have to keep flipping back and forth. Let me just real quickly, there you can see charge 1 is in the upper left and charge 4 is in the lower right, and charge 4 is a -1 and these others are positive, and they're at the corners of a square with side length of d. This is going to help us when we write the equations in the rightmost column here. We have Q1 already in there in the system. Now we're going to drag Q2 into this. And when we do that, we're pushing charge 2 into place. And you can see that the electric force is going to fight us when we do that, which means the work that the electric force is going to do is going to be negative in sign because the electric force will be acting in one direction, but we're forcing the charge to move against that. So the work done is negative, and the electric potential energy change, therefore, will be positive. Let's go ahead and fill in these first two columns for all of these. Now, if we bring in charge Q3, which is up here, you can see it's positive, as are charges 1 and 2. Charges 1 and 2 are already in the system. When we bring in charge 3, with regard to charge 1, the electric force will do negative work, which means the change in potential energy will be positive. Similarly, with charge 2Q, there's going to be negative work that the electric force does, and that means that the potential energy change will be positive again. Now we're going to bring in charge 4. And when we bring charge 4 in, you can see that there's an attraction between this one and, let's say, charge 1. So the electric force is trying to draw these closer together. Remember, I'm bringing 4 in from infinity. And so the electric force is doing positive work. Charge 4 here is moving in the direction that the electric force wants it to go, which means that sign is going to be negative. Similarly with these other two. In each case, when we consider charges 1, 2, and 3 individually, the electric force will do positive work whenever charge 4 moves into place. Charge 4 is a negative charge, and therefore the change in potential energy will be negative. And this is something that you might have studied in mechanics. Whenever a conservative force does positive work, the change in potential energy is negative. It decreases. So the equation for the potential energy between charge 1 and charge 2 would look like this. Potential energy associated with those two charges is going to be K, Q1, Q2 over the distance between them, which is D. These charges, remember, are at the corners of a square of side length D. And that is going to be a positive number. That's what we just wrote down in this column right here. What about between charges 1 and 3? Well, same sort of a thing. The potential energy between just those two would be K, Q1, Q3. Now, what's the distance between charges 1 and 3? Up here at the top, corners of a square of length D. That's a positive number. Q1 and Q2 are positive charges, and they have an energy associated with them that is positive. We follow the similar pattern here. 2 and 3, K, Q2, Q3. Now, what's the distance between 2 and 3? We need to be careful here. These are at opposite corners, so it's not going to be D, is it? It's going to be root 2D, 45, 45, 90, right triangle. And those two charges are positive, and when you multiply two positives together, you get a positive number, just like that. What about when we bring charge 4 in? The potential energy between 1 and 4 is going to be K times Q1 times Q4 divided by, what's the distance between 1 and 4? Again, opposite corners of the square. So root 2 times D. And Q1 is positive, but Q4 is negative. So in the numerator, if you have a positive number multiplied by a negative number, that energy is going to be negative. Now, if we have 2 and 4, same sort of thing, K. Q2, Q4, what's the distance between those? That's just D. A positive charge, a negative charge, they're going to multiply out to give you a negative number. And finally, the potential energy stored between 3 and 4 is going to be K, Q3, Q4. What's the distance between these? It's a side length D. Q3 is positive, Q4 is negative, therefore U is going to be a negative number. By the principle of superposition, to find the potential energy associated with the 4-charge system of the figure, what would we do with the quantities in the rightmost column of the table? We would just add them up, taking into account the plus and the minus. But nicely, because energy is a scalar, we don't have to worry about angles, sines, cosines, doesn't matter at all. You might have done something similar to this when you were studying gravity, different masses, and each of the gravitational potential energies came out negative, and so you just ended up with a bigger negative number when you were all done. Here we have to be a little more careful, because with electrical potential energy, it could be positive, it could be negative. It depends on what the charges are